We're going to work some problems involving gravitational force. This is in section B of the student packet that is on page 9. Okay, the first problem asks us to calculate the gravitational force that the Earth exerts on the Hubble Space Telescope. So this is just an application of the law of gravitation, which we derived in the lab that we just did. And that formula says that the force of gravity equals the universal gravitational constant, big G, times the big mass times the small mass divided by the square of the distance between the two masses. Okay, so I'm going to plug in the values here, and as I plug in, I want to make sure that everything is in standard units. I already see that one value here, the altitude of the Hubble telescope, has been given in kilometers, and I need to change that to meters. So convert to meters. There are 1,000 meters in every kilometer, so I'm going to multiply that by 1,000 and get 612,000. Okay, so I think I see the mass of the Earth and the mass of the Hubble, but remember that r is not the radius. R is the distance between the centers of the masses, and I'm going to have to calculate that here. So R, in this sense, is the radius of the Earth plus the altitude of the satellite. And so that's going to be 6.38 e to the 6th meters, that's the radius of the Earth, plus the 612,000 meters, that is the altitude of the spacecraft. And so we have an R here of 6.992 e to the 6th. Okay, and that's in meters. So I think I've got the information to plug in. G is 6.67 e to the negative 11th. The big mass is the mass of the Earth, 5.97 times 10 to the 24th. Hubble's mass is 11,100. And then R, which is the distance between the two masses, is 6.992 e to the 6th. And I need to square the R there. Okay, so let's put this in a calculator. And I get 90,411 newtons. That's the gravitational force that the Earth is exerting on Hubble all of the time. Okay, let's just look at number 2. So here we have an asteroid orbiting the Sun, and it tells us that at some point in time the asteroid experiences a gravitational force of 3.14 times 10 to the 13th newtons, and so we want to figure out how far is the asteroid from the Sun. So since this involves a gravitational force, the formula is F sub G equals universal gravitational constant times the big mass times the small mass divided by the distance between the masses squared. And I'm really solving for that R in this case, right? So let me just bring that out by itself. R would be G big M little m over the force of gravity, and I need to take the square root of that. As I plug in, I want to make sure everything is in standard units. The big mass here is the mass of the Sun. Okay. And so if I do this math, I'll have this answer. And then don't forget to take the square root, and we get 4.112 times 10 to the 11th meters. There's one more problem that focuses just on force of gravity, and that is number 5, where we have a table here with 4 scenarios of a planet and a moon, and we want to rank the scenarios from the greatest gravitational force to the smallest. So in each row, we can calculate the force of gravity. It's going to be G times the large mass, which here in this first row is just big M, times the small mass, here it's small m, divided by the distance between them squared. So the distance here is d. Okay, so in the first row, that is the force of gravity. Don't be thrown off because you don't know values to calculate. I think you'll see in a minute that we're going to have enough information to rank them. In the second row, the force of gravity is G times big M. Now the smaller mass is 4 lowercase m. And the distance here is half of d. So I have to square the distance. So I have to square half of d, right? So that's going to be 1/4 d squared. If I bring out the numbers, I have a 4 and I have a 1/2 squared. And I'm sorry, I forgot to put my squared here. Let me do that. I can bring those numbers in front of the the expression with all of the variables. So 4 divided by 1/4 is 16. So this would be 16 times G big M little m over d squared. So now I can see, the scenario in the second row is 16 times the force of the scenario in the first row. If I do that for the others, I'm going to get G times 4 big M times little m over d squared. So this one is just 4 GM over d squared. And in the bottom row, I have G times 2 big M times 3 little m over 2d squared. So this would be 6 is the number on the top, 2 squared, or 4 is the number on the bottom. 6 divided by 4 is 1.5 G big M little m over d squared. Now I can rank these. The largest is this one, the second row, with 16 times GMMD squared. The third row is the second biggest, the bottom row is the third biggest, and the fourth row was the smallest.